In experiment number 8, we're going to use VSEPR theory to predict the molecular structure of molecules in 3 dimensions. Then we're going to use this Spartan Student Edition software to draw the molecules and to probe their bond angles and bond lengths and to determine their dipole moments. I will illustrate how to use Spartan for the example SOF4. First, you want to go to the File menu and then choose New Build. Next, you'll want to click on the Inorganic screen over here. Then click on the element carbon and it'll give you a pop-up periodic table. In SOF4, sulfur is our central atom, so we'll choose sulfur. Then we need to choose the correct electron geometry. For SOF4, it's the trigonal bipyramidal electron geometry, which the British program calls the bibent trigonal. So select that, and then double-click in the blank portion of your screen. You can now move the molecule around, and you can see that now I'm looking down the axis. And here I've oriented the molecule in the normal fashion, with the north and south poles along the axis, and these 3 in the equatorial plane. Next, we'll want to put on our ligands. So we'll go back to the inorganic menu, choose our periodic table, and we'll put on our fluorine ligands. So we choose fluorine. Because these are terminal ligands, we then choose this, which is the single bond. And then we know our fluorines have to go on the 2 axial positions. So we just click on those, and on 2 of our 3 equatorial positions. Next, we want to put on our oxygen. So we go back to the periodic table and we choose oxygen. We make sure we still have it on here. And then we can come and put our oxygen on there. Once we've drawn the entire molecule, we can click the View tool to highlight the whole molecule. We want to change our sulfur-oxygen single bond into a double bond, so we're going to click on that bond. Just click right in the middle of it to highlight it. Then right-click, choose Properties, and change it from single to double. Close this window, and click the View tool to highlight the entire molecule again. Now you can see we've drawn the preliminary structure of SOF4. Next, we're going to tell the program what quantum mechanical calculation we want to do. So we'll go to the Setup menu, Calculations. We want the equilibrium geometry in the gas phase. We want to use Hartree-Fock method 3-21G. This is a neutral molecule, so we'll leave this set at total charge of neutral. However, if this were the ICl4 minus ion, we would have to change it to anion -1. All the other molecules are neutral, so you can leave it as neutral. And we have no unpaired electrons in the molecule. It's not a free radical. So everything is set here. Now we're ready to submit the calculation. You can give it a name, and you can tell it where you want to put it, and then click Save. It'll tell you that the program has started the calculation. You say OK. Then we're going to wait for the program to do its calculations. A program is taking your starting input and changing all the bond lengths and all the bond angles individually until it finds the lowest energy conformation. This will only take about 10 to 30 seconds, depending on the molecule. Once Spartan has completed the calculation, it will give you a dialog box like this, and you just click OK. Next, you'll want to orient your molecule in the normal fashion. Notice that it's not exactly the same as it was when we drew the molecule in the first place. We have changed some of the bond angles and bond lengths. This is exactly what the purpose of the program was. Now we want to probe those bond angles and bond lengths. So we're going to go to Geometry, Measure Distance. If we want to measure the sulfur to oxygen bond length, we will click on the sulfur, hold down the Shift key, and then click on the oxygen. It'll tell you the bond length down here in the box at the lower right. So this is 1.407 angstroms or 140.7 picometers. you'll want to record all of the unique bond lengths in the molecule. So a sulfur to fluorine axial has a bond length of 1.577 angstroms, or 157.7 picometers. And a sulfur to fluorine equatorial has a bond length of 1.542 angstroms, or 154.2 picometers. Record all of the unique bond lengths in your notebook. Next, we want to determine the bond angles. So we'll go to Geometry, Measure Angle. Let's say we wanted to determine the fluorine equatorial to sulfur to fluorine equatorial. We'll select the atoms in order so that the center of the angle is the central atom. So we'll select the fluorine equatorial, hold the shift key down, select the sulfur, keep the shift key down, select the other fluorine equatorial. The bond angle is reported down here, 113.61 degrees in this case. We'll do this for all the unique angles in the molecule. So let's say we want the oxygen to sulfur to fluorine axial. We select those, holding down the shift key in between in the right order, and then we record the angle in our notebook, 98.28 in this case. Oxygen to sulfur to fluorine equatorial, 123.2. And then we got one more unique bond angle, and that is the fluorine axial to sulfur to fluorine equatorial, which is 85.47 degrees. So once we've recorded all the unique bond lengths and all the unique bond angles in our notebook, there's one more thing we want to do, and that is to measure the dipole moment of the molecule. So you'll click the View tool here to highlight the entire molecule. Then you'll go up to Display, and bring it down to Properties, and the dipole moment is listed right here, 1.34 dBs. So you'll want to record that in your notebook as well. If the dipole moment is 0, then the molecule is nonpolar. If it's non-zero, then the molecule is polar. You'll have to do this for each of the molecules that is listed in the lab. I've just done it for this one to show you an example. Let me show you a different example. So we'll do a new build. Let's say we wanted to do the molecule H2O. So we have oxygen selected here, and we know it's a tetrahedral electron geometry, so we choose tetrahedral. Double click in this space. If we click the View tool at this point, it'll put hydrogens on all the positions. Okay. We know we want hydrogens in 2 of the positions, but the other 2 positions are lone pairs. So what we can do is we can get the Delete tool here, and we can click on one of those spokes where we want to have a lone pair, and it'll get rid of the hydrogen and the spoke. And then we click the Delete tool again, and we get rid of our second one, and now we're left with the molecule. We can select the View tool to highlight the entire molecule, and then we can go and set up our calculations and do everything the same as we did in the previous example. I just wanted to show you how to draw this one so that you knew what to do and how to handle lone pairs in molecules. Okay, so you'll now be on your own to do all the calculations for the remaining molecules in the list